Hello, good afternoon. This is Joy. I'm your tutor for this particular workshop, uh, AI Vision and Design, and we will particularly focus on multi-style transfer using neural networks. I believe that the icon shows that only one person has joined. I believe that is what the icon means. It says one right next to the I. So probably I'm going to wait a few minutes till some more of the participants join us. I'm not sure how many of us are present at the moment. If you are indeed uh, in the session you've joined, then can you kindly type a yes or your name in the session chat? That way I'll know that there are enough of us for me to start the presentation. Hey, morning. I can see Omar and Giuseppe with us. Uh, Pardon me if I get your names wrong. Um, is there a way to know how many of the participants are online with us right at this moment? All right. Just give me a couple of minutes. I'll contact the IT support.
Yes, doctor. What's the problem?
Hi. Is there a way to know how many of the participants have joined the session? Because unless all of them have, I would wait for a few minutes.
7 participants.
All right. Hi. Is there a way to know how many of the participants have joined the session? Because unless all of them have, I would wait for a few minutes.
7 participants.
All right. Hi. Is there a way to know how many of the participants All right, I think since 7 out of 11 are present and others may be joining along the way, I am going to begin our session. I just have one more question, which is there a way for the participants to speak directly to me, or is it all through chat? Is the communication only through chat, or is there a way for the participants to talk to me? Do you guys have a share screen option at the bottom of your screens? All right, so they cannot probably talk directly to me. Okay, that's kind of opaque, to be honest. I am used to seeing faces and have audio conversation along with the occasional video connection. Anyway, nonetheless, I'll begin with a presentation where I'll cover the different learning styles within AI, and I'll touch upon the background of style transfer, and then we'll move on to the Google Colab link that I had shared with you earlier in the day, and we'll execute our multi-style transfer. If any one of you has not received that email or doesn't have the link to the Google Colab notebook and the Google Drive folder where we'll upload files for me to make the presentation, kindly type your name, rather kindly type your email address in the chat. I'll forward the mail to you. Having said that, hi, I'm Joy Mondal. I am the founder and design head of Research Lab. We predominantly work in India and Southeast Asia. We work as design computation consultants to other architecture practices, and occasionally we release software solutions. As you can see through the icons on the right, these are Grasshopper plugins that I've written, one of which, the first one, Chingri, generates Mondrian-inspired 3D forms, and the second one, Elish, automates the process of column beam placements on orthogonal floor plans. I am incidentally presenting Elish in this conference as well. My paper presentation is tomorrow. And at the same time, I happen to teach as a visiting faculty in a couple of institutes in India, SPA Delhi and CEPT University Ahmedabad. What I'm going to do through this presentation is address some very basic questions, some fundamental questions related to the business of artificial intelligence, machine learning, neural network. What are the different types of algorithms? How does neural network work? And finally, end the presentation after talking about style transfer. First fundamental question is, how is machine learning different from traditional programming? As you can see in the slide, in traditional programming, what do? We know the algorithm from the onset, or our tacit knowledge renders us the ability to note down the algorithm in executable smaller components. In other words, we know the rules of the algorithm and we have the data which needs to be processed. And through the algorithm, as an example of the traditional programming type, we get the answers. However, in machine learning, the connection differs a bit. We do not know the algorithm clearly. It's kind of a black box. What we do know, or rather what we do have, are two things. One being a lot of data, which would include the input variables and the output variables as shown in the image. Answers basically mean the output and data would mean the input. And what machine learning does is that it goes through those two variables and emerges out with the rules so that when we enter new inputs, corresponding output would be generated. So there's a fundamental shift between the process of working. In traditional programming, we offer the algorithm and accordingly output is generated. In machine learning, a bunch of input and output is fed into the program and the program generates the rules or the algorithm. Now, again, this is another pretty fundamental question. What are the differences between artificial intelligence, machine learning, and neural network? They are, in fact, nested within each other. That is to say, all neural networks are examples of machine learning, and all machine learning algorithms are examples of artificial intelligence. So the question becomes in which cases artificial intelligence programs are not an example of machine learning? Tasks or programs which kind of mimic human intelligence, however, do not use, uh, rather, do not make the program to generate the algorithm. Instead, uses a very extensive and complex algorithm which is made by the human, could be an example of AI, which is not part of machine learning. For example, the chatbots, which we see on many service websites, where you have certain options in the chatbot, you select the right option, and then you proceed with more options. Those examples are AI, which is exclusive of machine learning. Machine learning has also many algorithms which are not neural network. What does machine learning basically mean? It means that we're employing the machine to detect patterns between the input and the output and learn to predict new answers. And neural network, obviously, you guys must be knowing, is a highly advanced version of machine learning that uses a series of neurons, which are essentially mathematical functions, to learn to solve a task. Examples would be prediction of the movement of stock and suggestion of music based on your browsing history, and so on and so forth. So again, what kind of machine learning is not part of neural network, or in other words, which algorithms do not use neural network? These are two simple examples of those. The first one being regression, wherein given a set of data points, regression is used to extrapolate dependencies between either two variables or between one variable and multiple variables. Another example is KNN, which is used to cluster different data points. I mean, as you can see in the image, once a new data point, which is the blue dot, is added into the domain of points, it literally calculates the distance between the blue point and all the green points, and the blue point and all the orange points. And whichever distance is lesser, the blue point gets added to that cluster, which in this case happens to be the green cluster. So it's pretty basic, rather basic and obvious distance measure algorithm, which is not as sophisticated as some of the neural network algorithms are. Now, if I move on to the aspect of what are the different types of neural network learning algorithms, there are, all of them can be categorized into three categories. The first being supervised learning, the second being unsupervised learning, and the third being reinforcement learning. In the first case, a bunch of examples are fed into the system, and the system is also told which of those examples belongs to a certain category or a certain type. And through learning through those repeated patterns, the machine learns to predict new classifications. For example, in the diagram, if you feed enough number of dog and cat pictures into the algorithm, eventually it will learn to differentiate between the two. It will know which one is dog and which one is cat. In unsupervised learning, the data is not labeled, the input is not labeled, which basically means that the machine is not told that these are pictures of cat and these are pictures of dogs. All the pictures are fed together, and the machine automatically learns how many different kinds of pictures exist in the input. We can control how many types of divisions we want. If we, let's say, mention that we want to divide the input into two parts, then intrinsically the machine will divide it into dogs and cats. However, since it is not labeled, it won't know the labels. If, let's say, we divide it into four parts, then we'll have dog, cat, probably some images which overlap between dogs and cats, and another example would be some extreme images which may not look like a dog or a cat. Pictures from weird angles which cannot be categorized using the algorithm. The third case is pretty dissimilar to the first two. The third one, reinforcement learning, doesn't really use any data, so to speak. It basically has an agent and an environment, and the agent has to navigate through the environment through a set of actions, and with each positive action towards solving the case, it gets rewarded a positive point, and with each action which takes it away from solving the case, it gets a negative reward. So with those incentives of positive reward and negative reward, the agent's aim is to maximize the reward, and that's how basically it travels through the environment and navigates through the space. Now let me elaborate on these a little further. As from the example, you can guess that an example of supervised learning would be prediction of numbers based on a trend, and the other would be classification, like I mentioned, cats and dogs. And unsupervised learning would obviously be associated with clusterings and finding linkages between images or data points or text for that matter. And reinforcement learning, as the image demonstrates, is basically a robot or an agent which has to, for example, let's say, navigate through the maze and get out of the other side. Now, in this case, of course, the reward would be to get out through the green arrow, and the negative rewards, or rather, in other words, punishments, would be, let's say, A, if the robot hits a wall, or B, the robot doesn't reaches a point from where it cannot take a left turn or a right turn. So you repeat that process enough number of times, and it intrinsically learns how to navigate the maze. Yeah. So as I mentioned, examples of supervised learning would be risk evaluation and forecast sales. Unsupervised learning is used for giving us recommendations. As you will see in Netflix, each of our recommendations vary from one to the other. It depends on uh, which genre we watch, which kind of shows we watch, which actors we watch frequently, and so on and so forth. And the other particular use is to detect outliers or anomaly, wherein from a list of data, if one sort of pops out and doesn't sit well with the others, then that can be detected, which is used for, let's say, detecting cancer from x-rays, wherein we feed the system a bunch of x-rays which do not have cancer, and another bunch of x-rays which have cancer symptoms, and then the algorithm connects the two and extracts the features which demonstrate cancerous growth, and thus the anomaly is detected. And examples of reinforcement learning would be solving games, as I've already talked about, and the other will be the gigantic task of making self-driving cars. Now, I'll just share a short video. And this is an example, a pretty rudimentary example of the snake eating the brick. And as you can see, its movement is pretty random in the beginning. And the reward is to eat the red brick. And the moment it intersects with itself or hits the wall, it gets restarted. And as in how we go through more and more generations, as in how it learns intuitively the vector direction in which it has to move to reach the red brick, and at the same time the way it has to move so as to avoid intersection with the walls or self-intersection for that matter, it keeps on adding the points. And if I fast forward my video, as you can see, it has clearly sort of devised its own strategy to play the game. And as you can see, as in how we increase the number of generations, the overall score and the pace of solving the game keeps on increasing. So again, to revise, rewards are set and punishments are set. Reward would be to move closer to the red brick. Larger reward would be to have the red brick. And punishments would be any instance of self-intersection or hitting an obstacle or the wall. Arguably, the most famous example of reinforcement learning is the example of Google DeepMind taking on the champion of AlphaGo, who is Lee Sedol. This game is particularly complex because the number of moves that are possible on the board happens to be larger than or higher than the total number of stars present in the universe, or in other words, it's pretty close to infinite. And while playing against each other, not only did the reinforcement learning algorithm beat Lee Sedol, but in between, it used certain moves that were not seen by any human, or rather not played by any human before that particular point. And at the end of the game, after being defeated and being startled by what had happened to himself, Isidore ended up saying it's not a human move, pointing to a particular move in the last game. I've never seen a human play this move. So beautiful. Makes us start to introspect how applying reinforcement learning to different scenarios may extract patterns which are not unique to humans, and in fact through that lead to newer inventions or discoveries. And again, as an example, a very low resolution example of how reward system works in intelligent vehicles. There are three parts to it, as I mentioned. Number one is the reward, which needs to be that it needs to be safe and it needs to be comfortable. Second is understanding how the environment is, which in this slide is stated as the state. Basically, the car has to understand and see the driving environment, see the mutual distance between the cars, traffic signals, any pedestrian intrusions, and so on and so forth. And combining those two, it has to calculate an action, which would be the speed and the control of the steering. And once such a system is simulated over and over and over again, the algorithm becomes smart enough for it to be brought onto roads, which is basically what we're seeing with Tesla at the moment. Now I will get into a few examples of supervised learning, particularly in the case of designs and in the case of architecture. To revise, if you remember, supervised learning is where we give numbers and outputs or give images with labels, and we make the machine learn to predict the numbers with new inputs or to classify images based on their input labels. At the moment, supervised learning is used to crunch numbers, number one, like I mentioned, and number two is to detect images from the environment. And these can be used to simulate or quantify subjective feelings that are associated with the design. And what do I mean by that? Let me give you an example. As an experiment, what we did was we made a parametric model of the Absolute Tower by Mad Architects. And of course, because it was made parametrically or defined parametrically, we could vary the parameters to generate a lot of options. And once a lot of options were generated using different parameters as seen in this slide, so we varied the radii of the ellipse, how the ellipse could be turned into a rectangle in plan, how the rotation works, the slope of the rotation, if balconies are indeed added to the shape or not, etc., etc. So there were a total of 12 variables. Now, what we did was we extracted images of few design variants and got them evaluated for originality. Each variant was evaluated by 30 architects. And so we had a list of these values, the 12 variables and the originality score. And we fed this into a neural network to basically read and predict later on what would be the originality score of other options which were not explicitly scored by architects, or in other words, were not explicitly taken by crowdsourced data. What this basically means is what supervised learning does in terms of subjective design evaluation is that if you look at the graph, if you take only few of the examples from the entire domain space of solutions and get those few as shown in the magenta dots, get those few evaluated by the relevant crowd, in this case architects, then through supervised learning we can appropriate the nature of the rest of the variants as well. So what we did after that was we realized that since we basically have a system to quantify originality, we took the same options which we got scored by architects to non-architects, and then we trained a neural network through the originality scores of non-architects as well, to sort of compare how architects and non-architects see or look at design originality. And to our surprise, architects seem to be more lenient as seeing design options as original. Now, what could this mean? Again, I'm going back to this image. If you can, these are the same bunch of options. Some of the options which were simulated, which were literally scored by architects as well as non-architects. As you can see in this one, let's say the top right option, as far as architects are concerned, a lot of them tabulated it as original, but as far as non-architects are concerned, a lot of them tabulated it as somewhere in between original and plagiarized, which basically means when this was simulated for the entire option domain, it turns out that architects by and large, are more lenient at seeing design options as original. It could be argued that because we can observe and see the nuances between two seemingly similar objects, we tend to be more lenient at accommodating those nuances. And those nuances may escape known architects, which is why they may be more ruthless in terming a design option as similar or plagiarized. What other examples or research or projects can we do using supervised learning? This is another project that we are involved in at the moment, which is to quantify and assist urban designers in a manner that the perceived safety of urban vistas by women can be increased in interventions and new greenfield developments. Now, how does this work? How do we get the data? There happens to be an app in India called Safety Pin, which has been collecting data by women on how each space is perceived in the safety index. So as you can see in the image, there are a bunch of green dots, orange dots, and red dots. And if you click on each one of them, the exact score gets highlighted from a range of 0 to 10. And then for each of the GPS locations, you can use an image and then use image segmentation to extract what percentage of view you have to the sky, what percentage of facade opening do we have, how many people are on the street, what kind of cars do we have, do we really have obstructed urban view, or do we have a view which goes through and through. And once we extract those parameters and feed into an algorithm the values of the safety score, similar to what we did with originality, expected safety perception can be simulated. So when you're designing something new, what happens here? Within the same area, depending on which point you pick, different spot would yield a different safety score. And not only that, because the app is GPS based, different cities of India, or in fact, different cities of the entire world, if all the data is indeed collected, different cities would yield different safety perception for the same spot. Someone in India may have a different perspective of safety compared to, let's say, someone in UK. And that will be reflected in the safety score only because the data is crowdsourced. So the implications of this are that probably participatory urban design can be taken up by designers using such a method, wherein, let's say, each resident of the area where some intervention is to be done is given an app and asked to click images of places or submit images of urban areas which they feel is beautiful, and then once, and also at the same time, submit images which they feel is not beautiful. And then once enough data is collected through the collaborative app, the designer can run such an algorithm to extract features of urban design which are preferred by the residents of that area. And since it's crowdsourced, there's a potential of a paradigm shift. And how does the shift happen? It's a departure from the top down uh, prescriptions given by design experts to a more inclusive bottom up evaluation by the users, which would be using the design, or rather living through the design, instead of it being coming from a design expert. Now, I just pause to see if at all anyone has any question. Right. Yes, the session is indeed being recorded and it will be shared with you at the end. Right. So the question now becomes we've gone through the examples of various broad categories of neural network, one being supervised learning, which I'm revising again. Supervised learning, which has labels or we feed numbers and it predicts output for new set of numbers. Unsupervised learning, just a bunch of data, not labels. We just tell the algorithm how many classifications we want, and accordingly, it will classify those into different clusters or detect uh, patterns or paths or data points which do not sit well with the other data points. The third being reinforcement learning, where through a reward function and understanding how the environment around us is, be it obstacle or driving or playing AlphaGo or playing Snake, the algorithm learns to behave in the environment, and given enough number of iterations, it becomes smart in solving those particular problems. Now, how does a generic neural network work? Let's see. You must have seen images where you have a bunch of circles which are connected to the next layer of bunch of circles, which are then connected to another layer of bunch of circles. And in some cases, they are connected one to one, and in other cases, they're connected many to many. And there are various configurations in which you must have seen that image. Let's kind of decode how conceptually how it works. Let's say we have a problem at hand, which is we're playing the rock paper scissors game, and depending on an image clicked of our hand, the neural network needs to guess, is it rock, pepper, or scissor? What happens is it takes a low resolution image of, let's say, our hand, and of course it's made up of pixels, and then those pixels are connected to a bunch of functions in the next layer of circles. These functions are basically the neurons of neural network, or these functions are basically the circles that you see in any image of neural network. Now, these functions start randomly. They do not have any specific set value to begin with. And the job of the neural network is to predict the output. For example, for rock, paper, and scissors, the possible outputs are, of course, rock 100, paper 010, and scissor 001. So if everything is random and if it goes thrice, there's a possibility of 1/3 for the right answer, or in this case, rock, to be guessed. And because it's random, there might be cases, or there must be cases, where the guesswork is wrong. The answer doesn't connect it to rock. Maybe the answer connects it to paper. In that case, two different functions come into play. Number one being the loss function, which basically calculates how far or how close uh, the prediction is to the actual result. And depending on the calculation of the loss function, there's another function called the optimizer function, which then generates an informed guess for the functions to have different controls in the next iteration. And this keeps on happening time after time after time for 1,000 times, or tens of thousands of times, or even more, depending on the complexity of the problem. So, where in the first few iterations, the functions were completely random, and probably none of the answers it could guess correctly by virtue of calculating the difference between the predicted option and the calculated option. And based on that, by changing the weightages within the functions or the coefficients within the functions, it keeps on getting closer to the reality. The prediction gets closer to the actual result. This is also why we need a holistic list of data to train a neural network, because it needs to go through the process of making mistakes and gradually learning through those mistakes to reach towards the right prediction. So, going back to the example of the absolute tire exercise, wherein we calculated or rather mapped the originality of design variance with respect to the original design by and compare it between architects and non-architects. If that is to be uh, explained through the process of neural network, what really happens is that uh, there would be two kinds of inputs. One would be the variables x1 to x12, as you can see in the image at top. It's plan radius 1, plan radius 2, rotation, scale top, scale bottom, balcony state, etc., etc. These 12 variables, and a target value, which is basically the originality score, is fed into the system, right? And in the first run, for each of them, using random functions, originality is guessed, and then the loss function calculates the difference between the guessed originality and these actual originality values. And then in turn, the optimizer function adjusts the weights within the functions. And these, each of them have different coefficients and weights. It adjusts it, and the iteration and the loop goes again. Another set of guesswork. The delta reduces a bit. Again, weightage is changed using optimizer function, and then it goes on again and again and again. Which is why whenever you read any research paper related to neural network, you'll find something called accuracy of the neural network, which minimum acceptance rate is about 70%, and only in very few instances would someone reach to an accuracy of 95% or above. In most of the cases, people do not run the algorithm so long, or even in most of the cases where such an algorithm is used, an accuracy of 80 or 85% is often taken to be appropriate and acceptable. Right. So within the neural network, or rather the artificial neural network, the way or the number of hidden layers can vary. It could be just one, it could be 2, 3, 4. Some cases there are 37, 38, 50 hidden layers, and also within each hidden layer, the number of neurons, which are basically mathematical functions, could also vary. So there are two kinds of controls for the neural network architecture. First one being the number of hidden layers, and the second one being the number of functions in each hidden layer. Of course, there are other algorithms to figure out what should be the optimized architecture of neural network that is to be applied to the problem that we are trying to solve. Those are neural networks made to optimize the neural network that is to be applied to solve the problem. Now, departing from numbers, if we get into the business of talking about neural networks that deal with images, we have to talk about machine vision and convolutional neural networks. Neural networks which basically deal with images, which classify images or read certain features of images, are called convolutional neural networks. And whenever you Google such a term, you'll find such images wherein There would be a sample image, and then there will be a stack of boxes, stack of smaller boxes, a stack of even smaller boxes, and then towards the end you'll find the stack of the smallest boxes. Now, what are these? What do they mean? Let's look at them conceptually. If we have to represent all the images in the size that they are, then it becomes very difficult to process them, because images inherently are larger in size than numbers. Also, whenever we use images, we need to extract features. So as to say, for example, we have, let's say in face detection, we have to extract eyes, nose, eyebrows, and lips. In this particular example, let's say the pixel values of the nail are the ones that are shown in the slide. Those pixel values are not directly taken into the calculation. A convolutional filter is added to those pixel values, wherein each corresponding pixel is multiplied by the given filter. And these are statistical methods which basically, once the multiplication happens, as you can see, the feature of the image start getting extracted. It basically loses some of the noise that an image may have, and through multiplication of certain convolutional filters with the exact pixel values, features start getting extracted. And I'll go back to this image. That is basically what these images also mean. Start in the first layer, it says convolutional XYZ, depending on the kind of algorithm you're using, which basically means it's getting multiplied by a certain filter, and through that some features are extracted. But this helps in feature extraction. Convolution helps in feature extraction. This doesn't inherently reduce the size of the files, or doesn't inherently reduce the time needed for computation. That is taken care by another function or another trick called pooling. Now, if you look at the matrix on the left side, you'll see, let's say, a bunch of pixel examples. That matrix is broken into 4 quadrants. The top left quadrant is shown at the top of the middle column. And from each of those quadrants, the pixel with the highest value is selected, and then a new smaller quadrant is made with just one value in each quadrant. So we're reducing 16 values into 4 values, which is called pooling. And as an example, the moment we execute pooling on the image, the feature extracted image that we saw in the previous slide, what you'll notice is that not only is the size of the image reducing in terms of computation, but the features are also getting enhanced. This happens because the selection of the pixel, as you can see again in this slide, the pixel which is the highest gets selected, which basically means the difference between the lowest and the highest pixels get enhanced, or the bands where the features are existing gets more enhanced. And that is exactly what you'll see in these images. First step is convolution, then the next step is pooling, then again convolution, then again pooling, and then you go on doing it. And if you notice closely into the images or the stack of images, this gray area connected into a ray into a gray point basically highlights that where one part of the input is selected and squeezed into a smaller portion, then again a part of it is selected and squeezed into smaller portion again, and that process keeps on repeating. And by the end of the process, we end up having an image which is significantly smaller in size and also with significantly enhanced feature compared to the original input image. All of these steps, if done once, will not yield satisfactory result. The trick is to combine such smart maneuvering with the power of computation, wherein for each concept, the iteration number is high enough to get rid of the errors and sort of go towards the optimized peak. Now again, going back to the example of rock, paper, and scissor, if it has to be read using convolutional neural networks, if it is broken down into smaller images and only certain features are extracted, we don't need to read the color of the hand, or if nails are present or absent, or if lines of the skin are present or absent, or if there are freckles inside the palm, etc., etc. If we divide it or convolute it enough number of times, all we need to observe at the end of the day is the number of fingers, or rather the number of extended fingers. If there are no extended fingers, it basically means rock. If all the 5 fingers are extended, it means paper, of course. And if only the 2 fingers are extended, it will mean scissor. Now, coming back to the last bit of the presentation, which is actually the topic that we're going to cover through the exercise. What is style transfer? We've seen the examples of numerical maneuvering through neural network. We've seen examples of convolutional neural network. Now let's talk about style transfer. Style transfer, as you may have read in the workshop brief, basically takes a content image, which basically provides the geometry, and it takes a style image, which basically provides the texture and the color, and then combines the two such that the target image has the content of the content image, or the geometry of the content image, and has the style of the style image, or in other words, the color and texture of the style image, which is what you see in the example over here. The style of the oil painting is being projected onto this solid hatch, and as an output of style transfer, you see the larger square, wherein not only is the color being transferred, but also the texture and the stroke widths are being transferred onto the solid hatch or solid block. So the next question is, what is multi-style transfer? It's conceptually the same, except for the fact that instead of one style image, multiple style images are used, and the final output will have a combination of styles of both or multiple style images. As you can see in the example, the content image remains the same. However, in this case, we used 2 different style images, one being a painting and the other being a black and white image. And as you can see in the output, it combines the tessellations from the black and white image and the hue and the pastel texture of the painting. So style transfer is not only used for making, or rather generating graphics for, let's say, design presentation, or for transferring one art image into another, but it can also be used to speculate the style of a plan had it been designed by another architect or had it been made in another style. For example, if you look at the top left image, that is a content image, and there are three different styles. The first one being Corbusier's design, the one in the middle being Charles Correa's design, which is pretty orthogonal, and the third one is an example of a Palladian villa, where as a feature you can see a lot of steps that go out towards the four sides, and you can clearly see in the output the first one. First of all the three outputs have stopped exhibiting the purely circular graphical style that the original content image had. In the case of Corbusier's example, the walls tend to exhibit the thickness that the original the style plan has. In the second example, the circular walls start getting pixelated, and because there are orthogonal lines predominantly in the style image, certain dummy walls get extended from the plan. And in the third one, because stairs happen to be a feature of the Palladian villa, a combination of aggregates of stairs get added to the output image. When we are to execute this, the only thing we need to be careful about is that the images need to be pre-processed in Photoshop or a similar software, wherein we need to delete unnecessary objects like furniture, because remember, as we saw in the slides, and I'll go back to this. Feature is extracted by the mutual difference between the pixel values in the neighborhood, which basically means if you add unnecessary furniture line or any line for that matter, those lines will also be considered to be a part of the stylistic expression or the content of the given image, and accordingly the output will also change. So for example, in the Palladian villa, let's say had we deleted the stairs, the addition of stairs in the output would not have happened. So we need to be careful about what sort of information we keep in the image for it to get processed. This was an example where the content image was the same and we varied the style. In this example, the style image remains the same, an oil painting. The content image varies, wherein on the right hand side it's a linear, straightforward, solid hatch, and on the left hand side is an example of a radial hatch. And as you can see in the output, that difference in content gets pretty clearly reflected. In the case of the radial hatch content image, there are obvious grooves in the output, and the grooves in a way guide the way the strokes from the style image are added into the output. And whereas in the case of the regular solid hatch, the paint is kind of smudged all throughout the surface of the hatch. So again, you vary style, of course the output will be different. And within the same content image, if you vary something as seemingly trivial as the gradient or the direction of the gradient or even the amount of the gradient, the output will be completely different, because again, like I mentioned, the features are extracted, the features are read by virtue of comparative difference with your neighbor. So to summarize, how does style transfer work? Of course, it uses convolutional neural networks, which we've covered previously. What style transfer does is that we do not need to use, or rather, we do not need to train a neural network from scratch. It uses a pre-trained neural network, the details of which I'll share with you when we move on to the Google Colab part of the workshop. And that network is trained to extract features, content features, as well as stylistic features from images. So what happens is that the process, or rather the iteration, begins with a noise image, the content image, and of course the style image. And as in how more and more iterations happen, the aim of the network is to reduce the difference between the content and the noise, as well as reduce the difference between the noise and the style. What does that mean? Let's look at an example. So on the top part would be examples of how the style is reconstructed. Starry Nights is the painting which is used as style, and the bottom part shows you how the content image is reconstructed. As can be seen in the style reconstruction part, right at the get-go, there's a huge difference between the noise added style reconstruction and the original style image. And with each iteration, the difference between them is reduced. So as we go towards the right, the noise added image gradually takes the shape of the original image, rather the original style image. However, in the case of content, it begins majorly with the image as it is. Only the corresponding style reconstructed part is superimposed on it, depending on where the features are. And then gradually, with more and more iterations, the effect of the style reconstruction becomes more and more evident on the content image as well. So in a way, with less number of iterations, the initial content remains exactly the same, and with more number of iterations, because the style reconstruction gets closer to the original style image and that interacts with the content reconstruction, with more number of iterations, the content reconstruction goes closer to the style image as well. Or in other words, the style is being added to the content image. Of course, keeping in mind or with regard to the geometrical features or the physical features of the content image. This is demonstrated in this slide, wherein the tortoise happens to be the content image and the famous wave painting happens to be the style image. And in iteration 1, if you zoom in enough, you'll notice noise. It's not, I guess, perfectly visible in iteration 1 in this slide. And like I mentioned, as you go on increasing the number of iterations, the difference between noise and style image reduces, which is why the style representation gets superimposed on the content representation in a better manner. And as we keep increasing iteration, the effect becomes more prominent. However, as can be seen in the iterations and in the graph at the bottom, increasing the number of iterations does in fact add more more stylistic feature onto the output. However, it comes with a diminishing rate of return, wherein in the first few iterations, the loss, which is a sum of content loss and style loss, will be reduced significantly. And as we keep going on beyond a certain number of iterations, the difference won't even be visible to the naked eye. Pretty self-explanatory in this slide. So difference between iteration 1 and 101 is pretty high. 101 and 201 is noticeable still, but towards the end, difference between iteration 801 and 901 is hardly recognizable, and you can hardly see any difference. There's another set of controls for style transfer, which are the content weight and the style weight. The images at the bottom half of the slide tell you which is the style image and which is the content image, and the series of images in the top half basically tell us how they interact with each other with changing weight. On the left side, the style weight is more, which is why you see more of the original style image, and towards the right, gradually the style weight is reduced and the content weight is increased more than the style weight, which is why you start observing the geometry of the content image being visible. Now, lastly, what about the tools? What are we going to use? We are going to use Google Colab, which basically uses Jupyter notebooks. Now, what are Jupyter notebooks? The Jupyter notebooks are basically web browser based notebooks which have a combination of texts and codes, and at the same time they can use or they can extract codes written and saved in GitHub, and usually they run locally, or one has to pay one cloud service or the other to run Jupyter notebooks. Jupyter notebooks are capable of using TensorFlow, which basically is a collection of open source library which are particularly used to develop and train machine learning models. So what Google Colab does is it hosts a Jupyter notebook, which of course is inclusive of GitHub codes and TensorFlow libraries. But instead of us having to run the code locally, which will take a lot of time because we're talking about very computation heavy work, or alternatively, instead of making us pay for the cloud service, Google Colab connects Jupyter, GitHub, and TensorFlow with its resident GPUs and basically provides us a free cloud GPU system along with the notebook hosting. I particularly picked this platform or these combination of tools for us because, like I mentioned, A, it's free, B, it's perfect for use as far as using pre-trained neural networks are concerned. Also, it's perfect for use if you are to train a neural network with only numbers. If you are to train a neural network from scratch with images, then Google Colab will not be suitable for your use because it tends to have an 8-hour to 10-hour direct connection limit. And at the end of the connection, you lose all the training that your neural network may have had. And if you cannot complete the training, you cannot save the model, and then you cannot use it later on. So for this particular case, for the use of multi-style transfer, Google Colab happens to be the perfect platform for us. Now, what could be the applications of single style transfer or multi-style transfer? We could map style plan onto content plan. Again, similarly, section to section, you can map paints to solid hatch, like the example we saw. We can map paints to 3D views, or map 3D views to 3D views, or map patterns to elevation, patterns to 3D view. And of course, we can map a map onto another map. Let's say we take the top view of a block of Barcelona and then use that style to map onto the content image, which is, let's say, the top view of Venice. Because the geometries and the patterns are different, probably it would yield an interesting result. I don't know. That's the fun of the process. Right. So now we are done with the presentation. If you have any questions, please type in your questions. All right. Let me just. There's nothing added in the questions tab. In the session chat, you can add questions if you want to. And we'll take a 5-minute break before heading on to Google Colab. Is there anyone who did not get the links to the Google Colab file or the Google Drive folder that we shall be using? All right, so I'm going to take a 5-minute break and then we can start with seeing how the neural network can be used to execute style transfer.